So let me. So this is actually kind of very special model of information geometry. But what I like to do in this talk is actually to give something like as in the subject of this session to connect information geometry and some special type of dynamical systems. And actually, the motivation can be explained something like this. So we can just look at some history of the information geometry, and of course, I mean, it starts from many people like Fréchet and Rao, and of course Fischer and many people. But I mean, now key idea from differential geometric point of view is first the Fischer-Rao metric and also the Amari chains of cubic tensor. And they play a very important roles in this area. And today we can find these techniques in a very, very standard textbook by Amari Nagaoka, or I, Jost, Lu, and Shibahen. But I mean, concerning about the connection with the dynamical system, there are some pioneering works by some Japanese people. And this was already mentioned in the previous talk, but in the 1990s there was works by Nakamura and also Fujiwara Amari, and they tried to give some kind of integrable Hamiltonian or gradient systems and from the framework of the information geometry. But in my opinion, there could be more interesting feature of information geometry which can be explored from the viewpoint of dynamic systems, especially from the viewpoint of Hamiltonian system or Lagrangian systems or something like an extension of these systems defined basically in the flavor of symplectic or Poisson, maybe contact geometry. But what I'd like to concentrate in this talk is actually what is called a statistical transformation model, which allows a kind of very beautiful symmetry of first about the statistical model and also about the resulting dynamical systems, which we will observe in the next pages. But this model actually stems from some seminal works by Barondov Nielsen and his collaborators, and today it's also found in his one of his textbooks. And also the idea is actually coming from some French researcher on statistics, Kazari, and some similar ideas can be also found in the famous text by Amari and Nagaoka. But I will explain the detail in the next pages. But before that, let me just give one page to review all the basic techniques of information geometry. So first, I mean, Fischer-Rao metric can be obtained whenever we are given with the manifold of samples, which are denoted by M, and the manifold of parameter, which parameterize a family of probability density function on the manifold M, which are denoted by rho here. And then the definition of Fischer-Rao metric is given by this. It's a 0-2 tensor on the space U, where with respect to the local coordinates theta, it's just given by this Gij d theta d theta I d theta j, where these coefficients are defined as expectation value of the product of two different type of the logarithmic derivative of the probability density function rho. And this has a very important meaning in the sense of statistics, because by the Graham-Rao theorem, it's actually giving rise to certain kind of lower bound for the variant and covariant matrix for a given kind of statistical inference. And as an analog, we can also go to expectation value of a product of three logarithmic derivative of given family of probability density functions, and it gives the notion of the Amari chains of Amari chains of cubic tensor, which typically is denoted with this kind of tensor. Yeah. And it allows to give some certain more deeper framework of information registry, namely the alpha connections and the dually flat structure when we take the value alpha equal to 1 or -1. So this is something basic, but in the, under the word statistical transformation model, I'd like to concentrate more specialized version of this. So namely, again, we are going to take a smooth manifold of samples, which I denote again by M, and then we assume there is a smooth action by Lie group on M. The Lie group is, of course, denoted by G. And we take a volume element on the manifold M. And we have to assume that this volume element enjoys a certain kind of invariant. In general framework, we can assume it's just relatively invariant in the sense that whenever we take two elements, one element in the Lie group G and one point in the manifold M, then the value of this volume form is actually evaluated as a product of the certain kind of character of a Lie group and the original volume form. So yeah, I mean, we can assume this, but in fact, in the later discussion, we only assume that this chi is just 1, meaning that the volume form is just invariant. But in any case, I mean, this is a kind of very general framework to cover many different types of family of probability density functions. Okay, and now this is sort of basic, but we have to assume that, I mean, since rho is probability density function, if you integrate it, then we always have value 1 for any choice of a point in the Lie group. And as a technical assumption, we have to also assume that the rho take always positive values. And it also enjoys what is called the relative invariance, which is written by this formula. Okay, and then okay, we can, I mean, whenever we have certain kind of random variable f, we can also take the expectation value of that. But it's actually important to point out that this expectation value EF is actually a function in G. So whenever we take this kind of expectation value for random variable M, we have certain certain function on the group. And of course, if we take just a constant function 1, and then we get 1. Okay, now let's move on to the definition of the Fisher-Rho metric, and it's done like this. So we are going to think about more infinitesimal version of the situation. So for that, we have to take the Lie algebra of the Lie group, which I denote by German G. And then for given member X of the Lie algebra, we can define the left invariant vector field on the Lie group. And then by a very straightforward computation, we can show that the expectation value of the logarithmic derivative of the function rho with respect to this left invariant vector field is actually 0. But if you take actually the product of such a kind of logarithmic derivative of the probability density function and take the expectation value, then it's actually not necessarily 0, but it's actually just constant with respect to any choice of the point in the Lie group. And this actually gives a notion of first the Fisher-Rho bilinear form on the Lie algebra, which is by definition given by this, and I denote with this parenthesis. And of course, if this is a bilinear form on the Lie algebra, so naturally we can extend it to the left invariant 0-2 tensor on the Lie group by the straightforward trivialization of the tangent bound to the Lie group. But what is important is actually this Fisher-Rho metric is not necessarily definite. And we will observe such a kind of situation in a more particular case. And as an analog, we can also define the Amari-Chensov cubic tensor. And this is, of course, first defined as a cubic form on the Lie algebra. And then it can be also extended to a left invariant as a free tensor by a straightforward method. And the definition is actually formally the same, but everything here is actually done in the framework of the Lie algebra, and everything is actually sort of left invariant framework. Now I would like to add one more formula, in fact, for the Amari-Chensov cubic tensor. And it's actually useful to compute in certain examples, which I will explain later. But here is some result to give some certain kind of different type of expression of this cubic tensor. And once our Fisher-Rho metric is actually shown to be just definite, meaning that it is giving a Riemannian metric, then we can define first the Levi-Civita connection for that. And using this cubic tensor, we can actually define the alpha connection by the formula written here. So alpha could be any choice, any real number, and particularly it's actually moved from -1 to +1. But anyway, this is actually giving rise to the general framework of the information geometry. Yeah, here's one remark. In fact, so when we have kind of degeneracy of the Fisher-Rho metric, we'll have maybe some problem because we cannot define, for example, the Levi-Civita connection. But nevertheless, under certain good conditions, namely assuming that there is a Lie subgroup H of the whole Lie group H, whose Lie algebra H has a complement on which our Fisher-Rho linear form is actually definite, then of course we have to assume something more. But I mean, H is compact. Then we can actually get some Riemannian metric, definite metric on the quotient space G over H. And this is actually basically formulated by the general result by Nomizu, given in 1950s. But using his theorem, we can even describe the Levi-Civita connection on this quotient G over H in a rather explicit manner, like in this formula. Yeah, so I mean, even though we lose, even if you lose the definiteness of the Fisher-Rho metric, there is still some chance to have certain kind of better situation to work on information geometry. Okay, now I'd like to move on some more particular case. Namely, from now on, I assume both the sample space and the parameter space are Lie group, the same Lie group, which is actually assumed to be compact, kept with the bi-invariant metric, which I denote by B. Here we can take the Haar measure on G, which is of course invariant. And in addition to that, I take Cartan subalgebra of this compact Lie algebra of the Lie algebra of the compact group, and it's also going to complement. So this is actually a kind of Cartan decomposition of the whole Lie algebra. And then we have to think about what could be a good choice of the family of probability density functions. And of course, there are many different types of choices. But here, we are sort of motivated by a completely different point of view. Namely, there is a result by Brocket and Ratu to describe the generalizer to the lattice equations in the framework of the double bracket equations. And they are using certain kind of description of the total lattice as the double bracket equation, but which is actually expression of the gradient flow on certain compact Lie algebras. And for that, in fact, of course, we have to have certain kind of objective function to have the gradient flow. And for them, the objective function is this one. It's actually coming from the choice of 2 points, Q and N, in the Lie algebra. And they are actually measuring the distance between Q, the inner product between Q and the adjoint transformation of that point N with respect to any point in the Lie group theta. Yeah, and then of course it's not enough because we want to have a decent family of probability density function, and our choice is actually just take this function f and plug this G inverse H into here and put it inside of the exponential function. And of course, divided by certain normalization constant, then we have actually a family of probability density function on the Lie group. And let's work on with this family of probability density functions. And then we can compute. First, we can show that this probability density function enjoys the invariance with respect to the Lie group action. And also we can compute the Fisher-Rho effects, in this case, semi-definite metric in a very, very explicit manner, which is given by this one. Here's some trick. In fact, I have switched from n to n prime, which is defined by this kind of integration formula, but in any case, it could be still, in some way, it's explicit. Here's one additional technical assumption that I have to assume that Q and n prime is sitting in the same Cartan subalgebra, but I think it would be something very, very technical and not really essential condition. Okay, now we have the Fisher-Rho semi-definite metric, but we can actually see that this metric is actually invariant with respect to the action of the Cartan subgroup, which has this German H as the Lie algebra. And it is actually, in fact, positive definite on the complement to this Cartan subalgebra. So this actually means that we can use the framework of the Nomizu to get the Fisher-Riemannian metric on the quotient space G over H. Yeah, so we can actually go to the definition of the Levi-Civita connection and also the geodesic flow for that metric. Or instead, we can also use the framework of the Lagrangian formulation of the geodesic flow. And in that framework, we can take this kind of Lagrangian function on the Lie algebra, and which can be actually extended as a left invariant function on the tangent bundle. Then we can deduce the so-called Euler-Poincare equation with respect to this geodesic flow with this, for the Fisher-Riemannian metric. And the final result for that is actually doing that. And of course, we can switch to the Hamiltonian side, and the equation is it's maybe rather easy to derive, but using certain kind of Legendre transform, we can get the Hamilton's equation for the same Riemannian geodesic flow. Okay, then there are some more things. Okay, so there are some framework to verify this deduction of the Hamilton's equation, which is called the Lie-Poisson equation, but Lie-Poisson reduction. But I don't really touch this, but rather I would like to move on the situation when we have really alpha connections rather than just Levi-Civita connection. So for that, we need to have some explicit formula for the Amari-Chernusov cubic tensor, and this is it. In fact, we can use the previous formula. We apply it in this specific case, and that's a formula. And using that, we can deduce the geodesic flow equation for the alpha connection defined, in fact, on the quotient space. And this is actually written at the level of the Lie algebra, but I mean, we have to focus on this. I mean, X is actually chosen from the complement to the Cartan subject. So this is actually kind of representative of the tangent space to this quotient space, O, which is equal to G over H. Yeah, so I mean, this is actually kind of general framework to give the equation for the alpha geodesic flows. But I mean, what I'd like to point out at the end of this talk is actually if we take a special value of alphas, namely, for example, if we take alpha just equal to 1, then the expression is actually turned to be very, very simple. I mean, originally we have two brackets, which is actually not, I mean, maybe impossible to merge to just a single bracket, but if we assume that alpha is just 1, then it merges to just a very simple bracket. And also, for the value alpha equal to -1, we have something similar, but there is actually some exchange between Q and A. And these two equations look like more similar to the double bracket equation, but there is some slight difference. I mean, the double bracket equation is usually on the right hand side, it should be something like this. But we have to add Q. And so there must be some connection with the generalized total lattice system, but for the moment I don't know. So maybe it's actually, we'll do this in the future works. Yeah. So I think I don't have time to conclude, so thank you very much. Thank you guys for and maybe one or two questions.
Thank you for a very nice talk on Lie groups. Very interesting direction. I was wondering, because in a group, in a compact group, there's only one invariant measure, which is the Haar measure. Yes, yes. So in reality, you're as you mentioned, it's more in the homogeneous space, and the counterpart would be the coadjuvant orbits. So in that case, you're dealing really Hamiltonians in a coadjuvant orbit, and I'm wondering if you had some kind of, from the Hamiltonian point of view, a physical interpretation of what this Amari alpha parameter is.
Yeah, well, okay, so it's actually a very nice question, but for the moment, I don't know the answer because I haven't worked on this alpha geodesic flows so much. But I mean, at least I can say that the system is already defined on the coadjuvant orbit, in fact. So yeah, this is quite near, but to interpret this, I mean, we have two terms. One term which is coming from the Levi-Jita connection, but the second term with the alpha questions, this is actually not easy to understand. Only maybe in the case alpha equals to plus or minus 1, like in the case of E or M geodesic in the standard frame of the information geometry could make sense. But for the moment, I cannot say anymore. But in any case, it's a very nice question. Thank you. I don't know, maybe one more question or not.
I have a question about the quantity that you call rho in one of your first slides. I mean, it should be the Radon-Nikodym derivative of the Haar measure with respect to the volume form, no? Yes. Yeah, no. Yeah.
Maybe this one.
Yes, but if you go to the next slide. I would expect something like for rho, like ecocycle identity rather than that. What is the meaning of that equation, in the first equation, I mean, for rho? Yeah. I would expect something like ecocycle identity, no?
Well, I don't know. I mean, I can only say this is just invariance of the probability density function. Yeah, cocycles. Well, maybe if you think about what is called relatively invariant function, then there is some contribution by some character.
Yeah.
It maybe has some interpretation as a cocycle. Possibly. But
I see. Okay.
Thank you. Is there any more questions? If not, then I'd like to thank everybody to come to this session. Thank you very much.